Good afternoon, pilot teachers, and good afternoon, students.
Good afternoon, Mr.
Okay, thank you. Sit down. Okay, from our lesson yesterday, we looked at information on hotspots, and today I'd like to recap on what we have covered already on hotspots. And we're going to move on also in our lesson today to looking at other features which are associated with volcanicity. And those features are extrusive features. From the beginning, when we looked at volcanicity, I gave the definition of pertaining to volcanic activities or the state of being volcanic. We started off by looking at intrusive features, which are formed as a result of solidifying of magma under the surface. We looked at features such as seals, dikes, batholiths, laccoliths, and also lapoliths. We also looked at the feature of stock. Then we moved on to extrusive features, and for the extrusive features, we concentrated mainly on volcanoes. We looked at the different types of volcanoes. We looked at what volcanoes are, how they are formed. And today we are going to look at other features beside volcanoes, which are also extrusive features associated with volcanicity. Before we go on to looking at other forms of volcanic activities or other features associated with volcanicity, we'll recap by looking at the definition of what hotspots are from our previous lesson. Okay, the definition that we have looked at already, we found out that hotspots are localities on the Earth's surface where greater than average thermal activity takes place, often leading to volcanic outbursts. Hotspots are thought to be the crustal expression of plumes in the underlying mantle and are believed to be closely related to the mechanism of plate tectonics. That was the definition that we looked at for what hotspots are. From that definition, the word plume appears. It is an important term because it is to do with the activity of magma under the surface resulting in the creation of the hotspot areas. So let's look at the word mantle plume. It is a term describing the mechanism in which rocks in the Earth's mantle begin to melt, thus becoming less dense and rising to the surface as the vertical component of a thermal convection current. This is thought to cause doming and finally rupturing of the crust at certain points. And the rupturing at the crust at certain points can also result in the formation of volcanoes. And that is the reason for why we also have isolated volcanoes which are not found on plate boundaries, and they can, or their explanation can be owed to the hotspots. We looked at an example of the hotspot volcanoes of Hawaii, and if we can make reference to that diagram again, we found out that the Hawaiian Islands, they are a chain of volcanoes formed where the Pacific plate is moving across a hotspot. And the movement of the plate can be seen as the volcanoes in the chain become older as you move northwards. In other words, the plate, the Pacific plate on which the Hawaiian Islands sit, is moving to the northeast direction or towards the north direction. And as a result of that, if we looked at the chain of islands in Hawaii, we would tend to find that the further away towards the north direction we go, the older the volcanic rocks are, and the main island of which the Mauna Loa sits on is the island which is directly now above the hotspots, resulting then in the formation of the active volcano known as Mauna Loa on that particular island. Okay, we also looked at other examples to help us understand the idea on hotspots in our activities yesterday. We had a map of the world, and that map of the world also showed us some of the isolated volcanoes of which the explanation can be as a result of the hotspots. Okay, so without further ado, we'll move on now to the lesson to the topic that I'd like us to look at for our lesson today, and that is looking at other features beside volcanoes now, which are a result of volcanic activities. Okay, those different features that we are going to actually look at for our lesson today will be features of geysers, we'll also look at fumaroles, we look at hot springs and lava plateaus. Those are the 4 features that we are going to look at, and those 4 features, as I've mentioned earlier on, they are also extrusive features which are associated with volcanicity. Okay, from the monitor here, we have an example of the first of those features now, and that is Aguissa. From the diagram, you can see there one of those famous geysers found around the world, and that photograph is actually showing the Lady Knox geyser, probably the most impressive in the Rotorua area, and that is in New Zealand. And note there it says that this particular geyser is actually prompted to erupt each morning by pouring soap down its throat. Okay, so here we have an example of what a geyser would look like. Maybe reference mainly to the steam or the water that is actually being released from that geyser, because a geyser, this would be the main feature that we look at to identify that that particular feature is a geyser. The releasing of the water to certain heights as a result of pressure which is built up under owing to volcanic activities. Okay, let's look at another photograph showing a geyser again, but this time the Old Faithful geyser, Calistoga, and note that this is in United States or USA. And here we also have the information to tell us that this particular geyser ejects steam every half an hour. So it will eject steam to certain heights, and then it ceases or it becomes dormant, pressure builds up again, and then the next half an hour, the releasing of the steam or the water again. But we have the 2 photographs there, or the pictures there, to show what a geyser looks like. We go back to the Lady Knox geyser, and then we have the Old Faithful geyser that's in United States or USA. Okay, besides looking at those pictures, we also need to know how those features are formed. We look at now the general structure that can also contribute to the formation of the feature Aguissa. The first diagram that we have there, of which you also have a sample or a copy of that on the worksheet provided, but let's look at the information from the monitor. Note there, first of all, water needs to actually get collected in a structure which is referred to as a cavern. How does the water get into this particular structure? It gets into the structure here under the surface through cracks on rocks. So when water is flowing on the surface, it can seep through the cracks in the rocks, and then when it is going through, it gets to be collected perhaps in a feature known as a cavern. The collecting of the water in this particular feature then will not form a geyser unless the area here is volcanically active, because the water will have to be heated up. And the heating of the water in this cavern here is as a result of volcanic activities. So the water gets collected, the water gets to be heated by the surrounding rocks, of which those rocks are closer to where volcanic activities are, resulting in them being hotter, resulting in them heating up the water. And then what happens is that when the water is heated, the water inside this particular feature known as a cavern here starts to circulate. What we are looking at here at this point in time is that the water in this cavern is actually at the dormancy phase. The geyser or the water has not been released yet. You also note that this particular feature, the cavern, has a restricted opening which will cause the steam to actually escape under pressure. But this is the dormant phase of that particular feature, the geyser. Let's look at the active phase now of that feature. So after some time, it will depend. It might take minutes, it might take hours for the heating up of the rock and the pressure to actually be released from the cave-in itself. So note here, it tells us that the pressure builds up until a jet of steam is ejected when pressure is actually reduced. And that jet of steam then forms the feature which is called a geyser. Okay, so this diagram here now shows us the active phase of the feature which is a geyser. So we'll go back again to those two diagrams. The first diagram shows us the dormant phase, but note water gets to be collected to fill up the cave-in here from joints or cracks in the rocks. Due to volcanic activities around where the cave-in is, the water gets to be heated up. Pressure builds up, and once the pressure is great within where the cave-in is, the steam is actually released in the form of a geyser. Okay, so those are stages in the development of a geyser, and we have the geographical structure of the rocks under the surface and the cave-in itself to have created this particular feature. Any queries or questions on that? You will be given an activity later on, and from that activity you will be required to make note of the diagrams as well as that to label your diagrams so that you know the stages in the development of a geyser. Let's move on. The next feature now that I'd like us to look at will be that of a geyser, but this time the geyser still based on another geographical structure rather than that of a cave-in. Okay, here we have a cave-in. We still have a geyser being formed, but rather this time instead of it being formed from a cave-in, a geyser can also be formed from an underground sump. And if you look at the sump, it is like a pipe which is underground instead of just one area like a cave under the ground, which is referred to as a cave-in. Okay, we're still on geysers, and this time an underground sump, of which that sump is actually connected also to a cave-in. Therefore, it is based on an underground cave-in and a sump. But we are not showing that cave-in. We are looking at the sump only. The area surrounding this feature is similar to that of the underground cave-in, but this time instead of a cave where the water is collected in or a round area where the water is collected in, we have a structure which looks like a pipe. The water gets to be collected in one of the sections of the sump. Pressure builds up. This is in the dormant phase of the geyser again, based on an underground cave-in and sump. The sump fills up with boiling water entering from the jointed rocks. Here we see the pressure is actually building up now, and in the active phase the water gets to be ejected as steam, and then we have the geyser again being created there. So these are the two different ways in which geysers can actually be formed, based on an underground cave-in and also based on an underground cave-in and a sump. Okay, with that information, we'll move on. This time, let's look at the second of those features, extrusive features, and this time we're looking at a fumerole. Okay, for a fumerole, this is basically looking at steam or gas which have been released from openings, like or as in the diagram given here. So whenever we have steam or gas which is actually released from the vent, then we can say that particular feature is a fumerole. So if you look at the example of the diagram given there, we have the pu'u or the pu'o vent, and here we have steam and gas which have been pouring into the sky since the current eruption started in January 1983. And it tells us there from that particular diagram also, Kilauea, which is a volcano in Hawaii, it emits around 2,000 tons of sulfur dioxide per day from this particular feature. Okay, we look at another diagram showing us a fumerole. Generally, the releasing of steam or gas from the opening as a result of volcanic activities will give us a feature known as a fumerole. Associated with fumeroles, we also have the other feature known as Sulfatara. The general formation of the feature of Sulfatara is very similar to that of a fumerole. The main difference then will be, note, in Sulfatara, steam is actually being released also from the openings on the earth's surface, but you can identify a Sulfatara from a fumerole simply from looking at the surrounding of the vent. If you find that around the surrounding there is a lot of yellow sulfur deposits, then we give the term to that feature as a Sulfatara. So instead of a fumerole and instead of only gas and steam being released, what might happen is that that particular opening might contain a lot of sulfur, and those sulfurous gases, when they get to be deposited in terms of the fine particles released and settle around the opening, they might make that vent, the opening of the vent there, yellow in color. And when you see the yellow or the yellowish color, then you can say that feature is a Sulfatara. Okay, so we have a photograph there showing us a Sulfatara. Another photograph also showing the feature Sulfatara. Let's look at the formation of Sulfataras and fumeroles. The diagram here showing us, again, water gets to be collected in cracks underground, gets to be stored, but this time the difference between the Sulfatara and the difference between Aguissa would be the water is not ejected to great height. Rather, it's only steam and gases which are being released. Okay, and that's the difference between fumeroles, Sulfatara, and Aguissa. If we look at fumeroles, in fumeroles, it's usually steam which escapes continuously under low pressure. So the continuous escaping of steams will give us a feature known as fumerole. But note, if the steam or if the area surrounding where the vent or the opening of this feature is contains yellow deposits of sulfur, then that feature becomes a Sulfatara. Any questions on that, features of fumerole and Sulfatara? No questions? Okay, we'll move on. Next feature, hot springs. Okay, we'll look at some examples of hot springs around the world. And we have there the Miichi Onsen, which is a hot spring at Hokkaido in Japan. You can see the water flowing there, the hot spring and the water. Not the brown, what here, the water which is flowing down, okay? We also have another hot spring. That's Tochi Onsen at Morioka Prefecture in Japan again. Papua New Guinea, do we have hot springs? Yes, definitely. In a lot of areas around Papua New Guinea where there are volcanic activities. Milne Bay, in Milne Bay, there's a lot of hot springs. In West New Britain, there's a lot of hot springs. Even in New Ireland, there are hot springs. Let's look at how hot springs are actually formed. Okay, similar to what we've done on geysers, fumeroles, and Sulfatara, we look at generally how hot springs are formed. It is important for us to note the structure of the rocks under the surface. Generally, you have the rocks that will allow water to actually pass through, and also cracks on the surface that will allow water to pass through. The water gets to be collected under the surface here. Then you have the layer of impermeable rock that does not allow the seeping of water further down. Therefore, when water gets collected here, if the surrounding rocks are heated as a result of volcanic activities, you might have then flowing out onto the surface hot springs. Okay, so here the diagram showing hot water images from hot springs. Note, generally around the world, hot springs are actually used for bathing around the world. Perhaps you've seen information on Iceland. Yep, people use hot springs to bath in. Not only that, it is reckoned that the hot springs, because they contain minerals from the ground, can be good for rheumatism. That is mainly to do with a disease of the bones and the joints. You get into the hot springs and they might be able to help in terms of massage, healing up with the problem of rheumatism. New Zealand, a lot of hot springs. Iceland, they do use the hot springs for bathing or washing in. Japan also. Papua New Guinea? Perhaps not for swimming in, for hot springs in the country. Yes? Susan has a question.
Going back to the geysers, is there a cause for why caverns were formed, like a barrel structure under the ground?
Okay, we are going back to the work on caverns, so let's check. We're looking at, sorry, not caverns, but the geysers. We're looking at the question of, is there a cause for how the different structures are formed under the ground to make it perhaps a cavern or a sump? The way in which the rocks are actually created under the surface, if the rocks are soft, then what would happen is erosion can actually, or weathering, sorry, not so much of erosion, but weathering, can actually dissolve or eat up in terms of weathering all these areas which are the soft areas in the rock. So through the process of weathering, perhaps carbonation or solution, what might happen is that because the water itself, in contact with other acids, if we take rainwater coming in contact with carbon dioxide in the atmosphere, gives us a weak carbonic acid. And if that weak carbonic acid comes in contact with any rocks which contains limestone, then what would happen is that the weak carbonic acid dissolves that particular mineral rock, resulting then in caverns or caves being created. So the underground features, the way they are formed in terms of whether it is a cavern or it is a sump, will really depend on the nature of the rocks and the processes which contribute to the formation of those. It could be through tectonic movements that a pocket of rocks in terms of the space gets to be created, or it could be through the process of weathering that such structures are actually formed. And here we are looking at the continuous maybe flow of water which is in here, so we can expect that the water which is coming through here is contributing then to creating such features under the surface. Does that answer the question? Okay. Later on, when we look at information on weathering and erosion, we are going to actually touch on that a little bit more in detail. Okay, we're still looking at hot springs, and now we're ready to move on to the last of the features, and that is lava plateaus. We have a map here, a world map, and that world map basically shows us the distribution of lava plateaus around the world. Not all of them, but some of the main lava plateaus. The red color on the world map will show the names of those different plateaus. We're looking at America, the Columbia and the Snake River Plateau, this area here. Then we have the Parana Plateau, Patagonian Plateau in South America. Then we come to Siberian Plateau, the Mongolian Plateau. In India, the famous Deccan Plateau. Then we have in Australia, evidence of volcanicity in the young stage of the development of that particular area, the Kimberley Plateau. In Africa, Ethiopian Plateau, Drakensberg Plateau. These are some of the lava plateaus which have been created and are evident today around the world as a result of magma coming out onto the surface. If it doesn't follow a mountain or a peak, then it becomes plateau or basaltic plateau or lava plateau. If it follows a peak, then the feature becomes a volcano. If magma comes up onto the surface, it follows a peak in the form of a hill or a mountain, the feature is a volcano. We've already looked at volcanoes, what they are and how they are formed. But if it does not, that magma coming up onto the surface, if it does not follow the mountain or a peak, then it can come up onto the surface and spread out or solidify on the surface, resulting then in the formation of lava plateaus or basaltic plateaus. What is a plateau? What is a plateau? Like in the Sogeri Plateau, it's a high elevated flat land. So in the buildup of magma, when it comes out onto the surface and it solidifies, it might build up a high elevated flat area, resulting then in the formation of plateaus. And plateaus can be formed as a result of magma coming out and solidifying, or they can be formed as a result of tectonic movements. We have a photograph here showing the Colombian Plateau. But this is not actually the plateau itself. The photograph here is showing us some of the features which are found on that particular plateau, the Colombian Plateau. If you look at those features, just some of the features formed as a result of solidifying of magma on the surface. And if you look at those structures, they look like pillars. And here's an example of what nature can actually offer in terms of the scenery and the environment. Okay, I'm going to give you some work now to work on, and those activities should also, or I would also want you to complete those activities for your homework, but we'll start on with the activities in class. Whatever you don't, I would like that information to be completed for your homework. The activities are, from those 4 features which we have looked at, I would like you to discuss the formation of those different features. How are they formed? After your discussion, what I would like you to do is, into your exercise book, I would like you to explain with the help of well-labeled diagrams how each of those features are formed. And that's what I'd like you to work on. Do your discussions first, and then after your discussions, you can go ahead with individual work in your exercise book. I'll give you 5 minutes for your discussion, and then after the 5 minutes, we'll get you to construct your diagrams. Okay, that will also bring us to the end of our discussion. I'd like you to go off now with the work for the second part, whereby into your exercise book, I'd like you to ensure that you are able to explain how those features are actually created, and your explanation should be accompanied by well-labeled diagrams. Okay, class, you can stand up now. Okay, to the pilot teachers, our keyword for lesson 42 is geysers. Good afternoon and thank you, students.